All right, welcome to The Explainer. Today we're going to crack open one of the biggest secrets in linear algebra. It's a concept that reveals the true story hidden inside any grid of numbers. We're talking about the rank of a matrix.
So let's kick things off with this question. Look, a matrix. It's not just some boring grid of numbers, right? It's actually this incredibly powerful thing. It could be a system of equations, a transformation of space, even a whole network of data. And the rank? Well, that's the key that tells us just how much unique, essential information is really packed in there.
Okay, here's the game plan for today. First, we'll nail down what rank actually is. Then, we'll check out two really powerful ways to find it. We're also going to look at its other half, nullity, and see how they create this perfect balance. And then, we'll wrap up by seeing why this one little number is basically a master key for all kinds of fields.
All right, let's jump right in. To really get what rank is all about, we got to talk about independence. And no, not that kind of independence. We're talking about mathematical independence.
So imagine each row in a matrix is like a recipe. Now, if you can make one of your recipes just by mixing the others, well, it's not really a unique recipe, is it? It's redundant. Linearly independent rows are those foundational recipes, the ones you absolutely can't create from the others. They're the real building blocks. And here's the bottom line. The rank is just a count of those truly unique, can't-be-faked rows. It tells you the true dimension of the information packed into that matrix. So if you've got a 3x3 matrix but its rank is only 2, that's a huge tell. It means one of those rows is just a copycat, offering zero new information.
Okay, so how in the world do we actually find this magic number? Well, our first method, it turns us into a detective. We're going to go looking for clues, starting with the biggest one we can find.
So, the big clue we're looking for is a special number called the determinant. Think of it as a truth detector for our matrix. If the determinant of the whole thing is anything other than 0, bam, case closed. The rank is the full size of the matrix. But if that determinant is 0, that's our signal that there's some redundancy afoot. So we have to dig deeper, looking at the determinants of smaller chunks of the matrix, which are called minors. The size of the biggest minor that gives you a non-zero number, that's your rank.
Yeah, so for example, if you calculate the determinant for a 3x3 matrix and it comes out as 0, that's a massive red flag. It's basically screaming at you that those 3 rows are not all independent. The rank has to be smaller. It's got to be 2, or maybe even 1.
Now, being a detective is fun and all, but let's be honest. Calculating all those determinants can be a real headache, especially with bigger matrices. Luckily, there's a much slicker and frankly, way more elegant way to do this.
And that brings us to our next approach, which is way more powerful. Instead of digging for clues in the original matrix, we're just going to simplify the whole puzzle. We're going to tame it, transform it, until the answer is just staring us right in the face. Here's the really cool part. We can do stuff to the matrix, like add rows together or multiply them by a number, and even though all the numbers inside will change, the fundamental rank, it stays exactly the same. It's like rearranging the furniture in a room. The layout's different, but you still have the same number of chairs, right? So the whole goal here is to get the matrix into something called echelon form. It's basically a neat staircase-like shape. And for a 3x3, it's a super simple two-step trick. First, you use that top row to zero out the first number in the rows below it. Then, you use your new second row to zero out the second number in the row below that. This process just beautifully reveals the matrix's hidden structure.
And voila! Look at this. We start with that matrix on the left, we do those simple steps we just talked about, and we end up with the one on the right. See that bottom row? It's all zeros now. That's our redundant recipe, plain as day. The transformation exposed it.
And this is where the magic happens. Once it's in this beautiful, clean echelon form, finding the rank is the easiest thing in the world. You just count the rows that aren't all zeros. In this case, we have 2 rows that have numbers in them, and 1 row that's totally zeroed out.
So our rank is 2. Boom. Done. Simple as that.
Okay, so we've got the rank, but believe it or not, this number isn't alone. It's actually 1/2 of a beautiful, perfectly balanced equation that tells the entire story of the matrix.
Let me introduce you to the rank-nullity theorem. It's super elegant. It basically says that the rank, which we now know is the useful, independent stuff, plus something called nullity, which is the redundant, dependent stuff, will always add up to the total number of rows. They are 2 sides of the very same coin.
So you can think of it this way. Rank tells you how much useful information you have. Nullity tells you how much redundancy you have. Put them together and you've got the whole picture, the complete story of the matrix.
All right, so why did we just go through all that work just to find one little number? Well, because this isn't just a math problem for a test. This is a seriously practical, powerful tool.
I mean, understanding rank is absolutely crucial. Think about image compression on your phone. How does that work? Well, by finding the rank of the matrix that makes up the image, we can just toss out all the redundant info. That's the nullity, and only keep the essential bits. It's how complex systems get simplified to their core components.
And it gets even cooler. Rank gives us these fundamental laws about how information behaves. This rule right here, it's basically saying you can't create new, unique information out of thin air just by multiplying two systems together. The complexity of your output can never be greater than the complexity of your inputs.
So that leaves us with this final thought. If one single number, the rank, can peel back the curtain and show us the true size of a system, what other powerful secrets are just sitting there, hiding in plain sight in the numbers and the data